Hey guys, this is Carrie, and this is lesson 9 from Unit 11, and today we're going to learn about radians. So, where we left off last time was finding things like the secant of 240 degrees. So, it's always helpful to have a picture with these. So, 240 degrees, if we were to graph it, well, we know that every angle in the coordinate plane starts at 0 degrees, and then as it opens upwards, this would be 90 degrees, 180 degrees, another 90 would make this 270 degrees, and a final 90 would make this 360 degrees. And so for 240 degrees, that's going to be somewhere between 180 and 270. So we can graph it right here. So we want to find the secant of 240 degrees. Now there's a couple of things that are useful to keep in mind with this. One is, because we have no point on our terminal side, we can't use those coordinate plane formulas that we really like to use. So those are out. Another thing is 240 degrees is too big to fit into a right triangle as one of the acute angles. So the SOHCAHTOA formulas are also out. So the final option that we have is to find a reference angle. So to find the reference angle here, the reference angle is always between the terminal side. Actually, let me choose a different color than pink. I'll choose black. The terminal side is between the reference angle is between the terminal side and the x-axis. So we have either this one or this one as choices. But remembering that it's always an acute angle, this angle is too large. So that reference angle must be right here. So to calculate alpha, well, we know that this top section is a semicircle, so this top section is 180 degrees. We know that the whole angle is 240 degrees. So to find this alpha piece of it, we could do 240, the whole thing, minus the top half, and that would leave us with this little section right here. And so when we do that calculation, 240 minus 180, that leaves us with 60 degrees, and so alpha is 60 degrees. So the way that we use this is we know that the secant of 240 degrees is going to be very close to the secant of 60 degrees. So we use the wavy equals for almost equal to. But now 60 degrees should ring a bell. That should make you think about your 30, 60, 90 triangle. So 30, 60, 90, 1, 2, square root of 3. Okay, so secant is one of those ones that I don't really have dialed in terms of memorized. So secant is 60 degrees. Secant, if you go back to your notes, you'll see it's the reciprocal of cosine. So it's going to be the flip of cosine 60 degrees. So if we take the cosine of 60 degrees, that's going to be adjacent, because 60 degrees is our focus angle. So this would be opposite, this would be the hypotenuse, this would be the adjacent. Cosine is adjacent over hypotenuse. And so cosine of 60 degrees would be adjacent over hypotenuse. And when we flip that, we get 2 over 1 for secant of 60 degrees. 2 over 1 is the same thing as 2, so we can just write it as 2. But now the important thing to keep in mind is we need to know whether this is going to be positive or negative in order to make it the secant of 240 degrees. And so if we think about our all students take calculus, only tangent would be positive in this quadrant. Because secant is the flip of cosine, cosine should be negative 1/2 in this quadrant. And so we know that our answer has to be negative because it wasn't the tangent or reciprocal for tangent. Alright, prove that the cosine of 180 degrees is -1. So at first this one seems like it's going to be the same as the last problem. We create a picture of it. We label 0, 90, 180, 270, 360. We graph our angle starting off at 0, But then because it's 180 degrees, it opens up to form an angle like that. And so we really don't have any tools available to us at this point. 180 degrees is too large of an angle to fit in a right triangle, so SOHCAHTOA is out. It seems like we don't know any coordinates, so this one is also out. And because it's on the x-axis, we really can't find a reference angle for this, so reference angle seems out. But if you remember where we cut off the last lesson, what we realized was no matter how far out we go, we always find the same result here. So if we go out a distance r, then when we rotate it, this will be a distance r as well. Because we're on the x-axis, usually you won't be able to do this, but because we're on the x-axis, you can actually figure out the coordinates of this point in terms of r. Because this point is going left r, we know that the x-coordinate would be negative r, because we're going r in the x direction, but to the negative side. And then the coordinates of this point on the terminal side, it doesn't go up or down at all. And so the y-coordinate must be 0. Now this actually gives us enough to prove that the cosine of 180 degrees is negative 1. Because now we have coordinates for x and y, it reopens this formula set right here as a possibility. So we know that the cosine of 180 degrees is equal to x over r. So the cosine of 180 degrees is equal to x over r, the distance. R divided by r is 1, so we get negative 1. And thus, the cosine of 180 degrees must be negative 1. Proved it. So we saw last time that we could use the same idea to find all of the ones that were on the axes. So this isn't this problem, so let me just change colors. We found that for 90, we found it for 0, we found it for 270, we found it for 180. And that's going to be critically important in the next lesson. But in this lesson, we're going to look at something new, which is radians. So let's talk about it. What are some of the units that we use to measure distance? So distance is an interesting one. There's a lot of units that we use to measure distance. One that comes immediately to mind is miles. But so that might be useful when we're hiking or when we're driving. But if we were measuring, the length of a football field, we wouldn't use miles. We would use a different unit. We would use yards, because the football field isn't even a mile. Or if we were measuring the distance from the floor to the ceiling, we might find that feet would be a better choice. Or if we were measuring the distance maybe between two cells in biology class or something, we might find that feet is too large and we would use a different measurement. Maybe we would use meters or centimeters or nanometers or microns. There's all these different ways of measuring distance depending on the situation. And that's an important observation. I mean, no matter what units you measure the distance in, the distance between point A and point B is the same amount. How we express it is just different. So it might be 1 mile, it might be 1.66 or something kilometers, it might be 5,000 feet. All of these would be like equivalent situations. Not exactly. I'm kind of guessing with the equivalencies here, but the distance would still be the same amount. Just the number that we use to express it would be different depending on our unit choice. And that idea is true with angles as well. And so there's actually two different ways to measure angles that we're going to talk about in this course. And one of them you know already. One of them is degrees. And there's a couple of very familiar measurements when it comes to degrees, right? If you think about a 90-degree angle, we have a very intuitive sense of it. That's what 90 degrees look like. We also have like a pretty good intuitive sense for 180 degrees. That would be an angle that's open to form a straight angle. We also know that a full circle angle would be a 360-degree angle. And this is a perfectly good way of measuring angles, degrees. And you've been using it maybe since middle school, I think. Certainly since high school. But when you press that mode button on your calculator and you see you have to select degree, or you're in Desmos. Let's go to Desmos and take a look. You're in Desmos and you have to select degrees. The other alternative for measuring angles is radians. And radians are also pretty useful. So let's talk a little bit about radians. So radians are just another, or sorry, let me write this down. Just another unit for measuring angles. And, oh, I keep pressing this button. I never pressed that button, the magnifying glass button, before, but now that we're remote learning, I guess I keep pressing it. So this is just another unit for measuring angles. But if we're going to introduce another unit, you might ask the question, well, what's wrong with degrees? And in order to get to this question, you have to ask yourself a question, which is like, yeah, you've got a circle. Wow, that's a really good circle. You've got a circle. So why are there 360 degrees in a circle? And that's probably a question that, if I imagine kind of where my brain was in high school, I might not have ever asked. But it's a weird question, like why 360 degrees in a circle? It's sort of like, why are there 12 inches in a foot? It's something that we know, but we don't really question. And this actually has a really interesting origin. If you think about the number 360 degrees, it's very close to a number that has actual significance. But before we get there, just let's visualize it. There's 360 of these little degrees, each of these being a degree. I can't even draw a degree, it's so tiny. Why are there 360 of those in a circle? All right, so getting back to where I was starting. 360 degrees is really close to a number that has sort of natural significance. It's close to 365. And if you think about 365, that's important because it's the number of days in a year. And there is something cyclical about years, right? If you imagine each day going along as part of a circle, 365 days later, it's somewhat a nice connection that you're back where you started on January 1st after 365 days. And so years have this like cyclical kind of tendency because they sort of repeat the same thing year after year. So it makes sense maybe that there'd be 365. It turns out that the group of people that decided that it should be 360 degrees in a circle were actually called the Babylonians. And the reason why they picked 360 degrees is that they liked 360 degrees better than 365. Babylonians chose 360 degrees because they liked it better. And the reason why they liked it better was the symbols that they used for doing math were very connected to the number 60. And so because 360 was 6 60s, they kind of liked that. And so they just said, you know what, we know it's 365 days in a year, but we're going to make it 360 just because we like it better. And that's what's wrong with degrees. It's just an arbitrary choice that somebody said. There's 360 degrees in a circle. And there's no real reason why you have to rely on an arbitrary choice here. There is a natural way that you can measure angles in a circle. So let's try to improve on this random choice that the Babylonians made. So, answer each of the following questions. On the diagram below, draw in a radius of the circle. All right, so we've been talking radius for a long time. A radius is from the center out to the circle. So this would be one radius of the circle. So now the question is how many times do you think you can fit the radius around the circle? So if you took this length, maybe it's a piece of string now, and you imagine picking it up off of that straight line, and because it's a string, you can bend it. Maybe you could take one radius, and you could put that radius here. And that would be one radius of length. I want you guys to take a guess. How many of these radiuses do you think you could put one after the next in order so that it goes all the way around the circle? So write down your guess. Now we can't really take a scientific approach to this because there's no way that I can exactly measure a radius. But if we put a second radius, let's see how that does. Let's imagine that we pick up this string and this time it's green. So we lay it down around the side of the circle and maybe it gets us to here. And this would be a second radius. So now we've got two radiuses on the circle. Well, it turns out that we don't need to do this scientifically. We don't need to actually go through the process of laying out all of these radiuses, another radius here, because we actually have a formula that will tell us the answer to this. If you remember from maybe Algebra 2 or Algebra 1 or geometry class, the distance around a circle, this whole thing, has a name. The length around a circle is called the circumference. And there's a formula that connects the circumference to the radius. That formula is the circumference of a circle is equal to 2 pi times the radius. So if you're curious about this question of how many times can you fit the radius of a circle around its circumference, the answer is you can fit it 2 pi times because the circumference is equal to 2 pi times the length of the radius. So we can fit the radius exactly 2 pi times around the circumference. And that's because the circumference is 2 pi times as long as the radius. And you can actually see that. We've done 3 so far. A fourth radius would get us to maybe here. A fifth radius would get us to maybe here. That one's a little bit long. A fifth radius would get us to maybe here. So this was 4, this is 5, 3, 2, 1. A sixth radius would get us from here, maybe to here. And then you'd have this little piece of a radius right here. Well, let's see exactly what number 2 pi is. So if we do 2 times pi, that's 6.28. It looks a lot like we fit 1, 2, 3, 4, 5, 6, and an extra 0.28 radiuses on our graph. Okay, so because every circle has this property that you can fit the radius around it 2 pi times, what we're going to say is that the natural way of measuring angles is that we can fit 2 pi radians, with each one of these being a radian. Each one of these angles being a radian around a circle. So we're going to say a full circle takes 2 pi radians to complete. Because you have 1 radian, which is the angle it takes to make 1 radius. 2 radians would be the angle it takes to make 2 radiuses. 3 radians would be for 3 radiuses worth of distance around the circumference. 4 radians would be for 4. 5 radians, 6 radians, and then this extra 0.28 radians, so 2 pi radians in order to go around the entire thing. All right, that diagram got really complicated, but it turns out radians are actually pretty straightforward if you keep a couple of simple facts in mind. So one thing is let's fill in the following 2 facts about radians. 1 full circle is 2 pi radians, which is equivalent to 360 degrees. Let me write that darker. Whoa, I didn't even know there were other colors over there. Equal to 360 degrees. So if 2 pi radians is a full circle, and that's a little arrow to show that it's opening from here up to the full circle as an angle, then half a circle would be half as much. So if we do half of that, that would give us pi radians. And we know that half a circle is equal to 180 degrees. This is my favorite radian fact right here. It takes 2 pi radians to make a full circle, which means that it takes pi radians to make half a circle. So if we wanted to convert each of the following from radians to degrees, all we have to do is keep this key fact in mind. Because pi radians is actually 180 degrees, to figure out how much pi over 2 radians is, we can take, well, pi is 180 degrees, we can take that and we can divide by 2. Now we know that that is 90 degrees. And that makes sense. If pi radians is a semicircle, then taking half of that should give us 90 degrees. So pi over 2 radians is 90 degrees. All right, these ones start to look a little bit more complicated. Here we've got 3 pi over 2. And we can do this one the exact same way. We know that pi radians is actually the same thing as 180 degrees. So really this is 3 times 180 degrees divided by 2. And you can use your calculator to do all of that at once, but a neat trick here is we already know 180 degrees divided by 2. We know that that piece of it equals 90 degrees. And then we can do 3 times 90 degrees from this 3 here to give us 270 degrees. Let's do one more of these, or a couple more of these. Pi over 6. Well, we know from our key fact that pi radians is really just 180 degrees in disguise. So this is 180 degrees divided by 6. If you do the math on that, you can use your calculator, or you can do it in your head and you get 30 degrees. The same way, we know that pi radians from our key facts, pi radians is just 180 degrees. So we'll have 5 times pi from the problem. The pi is 180 degrees over 6. And so, again, you could just plug this all in your calculator, but I don't really like to use my calculator because I'm kind of lazy about getting it out and I like to do stuff in my head. We actually know 180 degrees divided by 6 already. We know this from the last problem. 180 divided by 6, that piece was just 30 degrees. And so we're left with the 5 from here. And if you put the whole thing in your calculator, you should get the exact same answer. It should be 150 degrees. And so right now what we're doing is we're practicing, we know 2 different ways of measuring angles. We are very familiar with degrees, we're less familiar with radians, but the same way you can convert from miles to feet, we can convert between the 2 different ways of expressing them. So on your own now, take a minute and try to do these, and when we come back, I'll give you the final answers. All right, so 11 pi over 6, that is final answer 330 degrees. This one, 45 degrees when you do the 180 over 4. This one, 225 degrees. This one, 120 degrees. To check your work, actually give yourself checks if you got them correct. If you got it incorrect, try it one more time by plugging in 180 degrees for each of these radian pi amounts. And you should be getting these answers with your calculator. All right, once you've got that completely set, let's take a look at our lightning round. So hopefully this works. Let's see. Dropbox, lightning round. All right, cool. Here we go. Oh, you're supposed to turn each of these from radians to degrees. So 3, 2, 1, go. So you're writing down the degree answer. So your final answer for this one would be 180 degrees. So you should have right here 180 degrees. All right, that's the last one I'm going to give away though. So try the rest of these on your own. And 3, 2, 1. 3, 2, 1. 3, 2, 1. And getting our answers, oh man, it put this weird symbol again. I don't know why it does that. It should be a degree symbol, not the one that's, not this symbol here. It should be a degree symbol. And this one, for problem 2, make sure you're checking your work. It should be 60 degrees, 300 degrees, and 54 degrees. All right, but there's a second round. So this time we're going to try to work backwards from degrees to radians. So your final answer here, well, it starts with 180 degrees. So every time you see this symbol, it's really the degree sign. My computer just doesn't format it correctly in that program. So 180 degrees is given to you. The final answer for this one is pi radians. So you're trying to convert it to radians. So your answers should all have pi in this case. "90 degrees becomes, what do you have to do to 180 to get 90? Okay, so pi, and then you'd have to do that divided by 2. Okay. And 3, 2, 1. And I didn't really show you a way to do that for these ones. So maybe you thought of some ways. For 90 degrees, well, if 180 is pi, what do you have to do to 180 to get 90? Well, you've got to divide it by 2. So if we do the same thing to pi, we find that 90 degrees is pi over 2 radians. For problem 7, we wanted to make 30 degrees. And so I always go back to my key fact, 180 degrees is the same thing as pi. Well, what do we have to do to 180 to turn it into 30? Well, dividing it by 6 will give you 30 degrees. And so if you divide pi by 6, you get pi over 6. And that would be your final answer here. Now the last one was a little bit tricky. This one was 150 degrees. And it's not obvious what number you have to divide 180 by to get 150. It's like a mystery to me. However, you can actually rely on your previous problem to help you out here. If you do 30 degrees, well, 30 degrees times 5 would give you 150. So if you do 30 degrees in radians times 5, you get 5 times pi over 6. And that absolutely does give you 150 degrees because this part was 30. 5 times 30 is 150. So this last row here was kind of like a tough stuff row. If you were finding that difficult, that's cool. We're going to keep working on it. But just sort of challenging ourselves with the material. So continuing on, kind of a natural question to me would be, we've got these 2 different ways of measuring angles. We're really good with degrees. Radians are pretty new to us. Can we do all the same stuff with radians as we did with degrees? And it turns out, yeah. Because they're measuring the same thing, just the size of an angle, you can do all the same stuff. So, in what quadrant does the terminal side of the angle 7 pi over 4 lie? Okay, I got no idea. So probably the step that you all should take whenever you see a radians problem is it's easier to think in degrees. So let's turn this into a degree problem. So to turn it into a degrees problem, we're going to do 7 from the problem. Pi radians is really just 180 degrees, and then we divide it by 4. If you put that whole thing in your calculator, 7 times 180 divided by 4. It doesn't matter whether the 7 is written separate or off to the side. We can rewrite it though if you like to have it look identical to the page. 7 times 180 over 4, 315. So this is really 315 degrees. Oh, in what quadrant does that lie? We know this. When we draw our quadrants, 0, 90, 180, 270, 360. Now that it's in degrees, we can just say it starts on the x-axis and it opens to somewhere between 270 and 360, which is quadrant 1, 2, 3, 4. And just for neatness, I wrote it with the Arabic numeral instead of the Roman numeral because it's easier to read. Sorry about that. My handwriting is pretty sloppy. All right, so guys, when you do practice problems here, you're going to be trying to find what quadrant these lie in. The first step is to turn it into a degrees problem because it's easier to think in degrees right now. Later on, it might be easier to think in radians, but for now, it's easier with degrees. So try these problems on your own, and we're going to review one of them when you've given it a shot. Okay, so let's take a look at problem 1a. For this one, I can't really think in degrees yet, so I'm going to convert, or radians yet, so I'm going to convert it to degrees. So this is 5. Pi radians is really 180 degrees divided by 3. We go to our calculator, and we do 5 times 180 divided by 3, and that gives us 300 degrees. So this is the same thing as 300 degrees. So if we were to graph it, this would be 0, 90, 180, 270. So 300 degrees, 360 degrees. 300 degrees is going to be somewhere in between these two. Okay. So the rest of these are part of your checkpoint, so I don't want to give them away. But if that helped you out and you weren't sure how to do B, C, and D, you can use that same idea to convert it to degrees by substituting 180 degrees for pi radians because those things are equivalent, so you can substitute back and forth. So give these a shot, and I'll check those when you turn it in. Of course, this kind of leads to one more question for today, which is, well, we can graph these things, but if we can graph them, can't we find the sine, cosine, and tangent, and all that stuff of these? So let's determine the sine of 5 pi over 6. Just like before, actually, this might be a little bit tricky of a problem. So we do know how to do these problems with degrees. So let's start by converting to degrees. Convert to degrees. So after that initial moment of hesitation, when we realize that we can substitute 180 degrees for pi radians because these are equivalent, we get the sine of 5 times 180 divided by 6. So let's do that. Oh, and actually, instead of doing the whole thing all at once, let's convert the angle. So this is 5 times 180 divided by 6 this time. That's 150 degrees. So this is going to be the sine of 150 degrees. Now you could plug this one in on your calculator, but you might get an ugly decimal for it. We do know from our do now how to do things like the sine of 150 degrees, though. It's very similar to problem 1, where we had to find the secant of 240 degrees. So what we're going to do for the sine of 150 degrees is we're going to graph it on our coordinate plane. So 0, 90, 180, 270. For the sine of 150 degrees, that's going to be right here. To find the sine of this angle, we used our reference angle, which is this little red angle between the terminal side and the x-axis, and it has to be acute, and that's why you know it's that side of the angle. Now together, 150 and the red angle make a full semicircle, 180. So in order to find the reference angle, we would say that alpha is equal to, you'd have to do a full semicircle minus the angle 150, and you get 30 degrees for alpha. Okay, so now that we've got 30 degrees for alpha, we know that the sine of 150 degrees, the one that we're trying to find, is going to be almost the same thing as the sine of 30 degrees. And if you draw your 30, 60, 90 reference triangle, 1, 2, square root of 3, you find that the sine of 30 degrees is opposite over hypotenuse, it's 1/2. And then you have to think, well, is it going to be a positive 1/2 or a negative 1/2 because of the quadrants? And so if we label those, all students take calculus. Students, sine is positive. So you don't have to write the positive because 1/2 just implies positive. But we know that the sine of 150 degrees is going to be 1/2. That's a 5. But the problem was given to us in radians. So it's nice to go back to the radians and we can say, well, sine of 5 pi over 6 must be equal to 1/2 because that's what the degree thing said. So to check your answer here, you can plug this in on your calculator pretty easily. Let me show you how. So if we do sine 5 pi, or sorry, 5, once we put the fraction in like this, 5 pi over 6, close the parentheses. It does give me 1/2, but yours might not give you 1/2. And the thing to keep in mind is now for measuring the angle in radians like we are in this case, then you have to be in radian mode. If you're in degree mode, you'll get the wrong answer. So if you're plugging radians in to your sine function, you have to be in radian mode. Now, I like to kind of always be mentally in degree mode and not rely on the calculator too much. So let's do one more example. Determine the cosine of 5 pi over 4. First step, convert to degrees. So in our case, 5 pi over 4 becomes 5 times 180 over 4. That's going to equal 5 times 180 over 4. If you plug that in on your calculator, you get 225 degrees. Let's just confirm. 5 times 180 over 4, yep, 225 degrees. All right, next up, to find the cosine of this, you need to graph it. So graphing it here, graphing 5 pi over 4, that's 225 degrees. That's going to be somewhere between 180 and 270, so 225 would be here. The third step, well, 225 degrees is kind of a hard angle to work with. So if we found our reference angle, which is going to be between the terminal side and the x-axis, so I've highlighted those pieces, the acute side of that would be this one here. So step 3, find the reference angle. And in this case, the top half right here, that's 180 degrees. We know that the whole orange angle is 225, so alpha must be equal to 225 degrees minus that top half, 180 degrees. alpha is equal to, if you do the subtraction here, 45 degrees. And that starts to telegraph the rest of the problem to us. For step 4, we know that the cosine of 225 degrees is going to be almost the exact same thing as the cosine of 45 degrees. To find the cosine of 45 degrees, we draw our reference triangle, 45, 45, 90. Well, that 90 is too bad. I'll just draw the right angle there, 90. 1, 1, square root of 2. Cosine of 45 is going to be adjacent, for this 45, adjacent over hypotenuse, so 1 over root 2. And next up, because all students take calculus, it's in the tangent quadrant, so cosine should be negative. And lastly, when we write our answer here, I like to go back to the radians. Cosine of 5 pi over 4 is equal to negative 1 over root 2. All right, so by doing this process, these 4 steps, you should give the next 4 problems your best attempt. And as you complete these checkpoints, make sure you take a picture and send your work in so you get full credit for them. And I'll give you some feedback if you don't get them correct, and you'll have a chance to revise them. So in summary, in today's lesson, we saw that there are 2 different ways to measure angles: radians and degrees. And it turned out that degrees were kind of an arbitrary choice. They just picked 360 degrees in a circle. Radians weren't so arbitrary. It was sort of forced on us by the circumference formula. There had to be 2 pi of them to make a full circle. But if 2 pi radians makes a full circle, that means that 1 pi radians, or just pi radians, would be 180 degrees. And the benefit of doing all of this stuff with radians isn't really apparent yet. It turns out that it makes calculus much easier when you work in radians. The formulas in calculus for derivatives, which you can talk about next year with Joe in AP Calculus, they turn out to be a lot better when you use radians than when you use degrees. So even though radians seem a little unnatural now and stuff, we're going to get really comfortable with radians this year. And I'll see you guys next class. Bye.